Today we're going to talk about the special right triangles and how they apply to right triangle trigonometry that we're going to be spending some time on to get you ready for pre-calculus. In geometry, you learned about two special right triangles, the 45, 45, 90 and the 30, 60, 90 triangle. The figures at the right summarize the relationships among the lengths of the sides of each triangle. Now, easier to remember with the song. 30, 60, and 90, it's very easy to see. The short side is 1, the hypotenuse 2, the other side is the square root of 3, and it's 45, 45, 90. These are easy to name, for it's 1, 1, square root of 2 in the triangle game. Now, the reason we do that is not because every single 45, 45, 90 triangle has sides of length 1, 1, square root of 2. It's actually showing a ratio between those sides. And what it means is, if we know the length of one of the two sides in the 45, 45, 90, and we want to get to the hypotenuse, all we have to do is multiply by the square root of 2, because this is like a little imaginary 1 out here. And vice versa, if we have the hypotenuse and we have to work backwards to figure out the length of a side, then we'll divide by the square root of 2. With the 30, 60, 90, what you always want to do is work your way to the short side, because the short side is the easiest way to develop what the hypotenuse and the longer side are. Because what we do with that is we multiply it by 2 to get the hypotenuse, and we multiply it by the square root of 3 to get the longest side. Now, working backwards, of course, you flip that around and say if we know the longest side and we want the short side, we have to divide by the square root of 3. And then once we have that, we can multiply by 2 in order to get the hypotenuse. If we have the hypotenuse, we can take the hypotenuse, divide it by 2, and get the short side, and then work forwards again and multiply by the square root of 3 for the long side. So you'll notice in their drawing up here that what they're doing is they're showing how if we just used variables instead of using the actual numbers, we have s's for these two side lengths, which form an isosceles right triangle, and then s square roots of 2 for the hypotenuse. And on the 30, 60, 90, whatever we have for the short side, you multiply times 2 for the hypotenuse and times the square root of 3 when you want the longest side. So these are two really, really important triangles that we are dealing with here, with the 45, 45, 90 triangle and the 30, 60, 90 triangle, because the trigonometry that we deal with, the major purpose is to get exact answers, not graphing calculator found answers that deal with the exact relationship between the sides of triangles. So when we look at A here, it says find the missing side lengths of each 45, 45, 90 triangle, and I notice the sides are each 5. And to go from a side length to a hypotenuse in a 45, 90, all we do 45, 45, 90 is multiply by the square root of 2. So y is 5 square roots of 2, and we're done. We go on to the next one. And then in B, a little bit tougher, and that's because they gave us the hypotenuse. To get there, you had to multiply by the square root of 2. So to work your way backwards, you have to divide by the square root of 2. And we must rationalize the denominator because, remember again, we want these to be perfect, exact answers. So on the top, we'd have 5 square roots of 2, and on the bottom, we would have the square root of 4, which is 2. And both of those x's would be 5 square roots of 2 over 2. And that's because in a 45, 45, 90, the two base angles are 45. And the converse of the base angles theorem that you learned in geometry tells us that the sides opposite those two angles will always be congruent. So that's why that's going to be isosceles. Now in example 2, we go after the 30, 60, 90 triangle, and I believe this is where I remembered to hit record. Like I said, the 45, 45, 90 is the easier of the two here. So let's look at the 30, 60, 90, and always think I have to work my way back to that short side, because if I have the short side, then it's really easy to get the other pieces. So example 2 says we're going to find the missing side lengths in this 30, 60, 90 triangle at the right. And I see that's all I get right there. So then I think, okay, short side to long side in the 30, 60, 90, you have to take it times the square root of 3. So if I need to work backwards, I'm going to have to divide by the square root of 3 to get my short side. Can't leave it like that. What do I have to do? Rationalize the denominator. So we'll get 4 squared root of 3 over 3. That's a big deal, by the way. You look at that and you go, gosh, that's a really ugly answer. But that's a perfect answer. That is a perfect answer for x. Okay, now I have the short side. To go from short side to long side, you multiply by the square root of 3. To go from short side to hypotenuse, you have to double it. So if I have 4 square roots of 3 over 3 and I double it, what do I get? 8 square roots of 3 over 3. Because when we multiply by 2, it's 2 over 1. You know, so all you have to do is double. Now if you're thinking, well, shouldn't it be the square root of 6? The answer is no, and you knew this, but it's been a long time since we covered this. Remember, integers are multiplied by other integers. Radicals are multiplied by other radicals. This is not a radical out here. This is an integer. So 2 times 4 is 8 square roots of 3 over 3 when we do that. So 2 ways to do that. Let's see. I'm going to make one up real quick. You can write it down if you want to. If this is coming easy for you and you don't feel like it'd be beneficial to write it down, then don't write it down. What should I go after first, x or y? X. How do I get it? Good. Now I have it. It's 8. What do I do? There it is. So, does this get ugly? Well, sometimes. You know, maybe when you divide it by 2, you get a fraction, a decimal. You know, we can't use decimals with these because we want our answers perfect. So you have to figure out how to write it with a fraction. But that's the 45, 45, 90, and the 30, 60, 90, which help us out tremendously when we start our work with the unit circle. So section 13.2 is about angles in the unit circle, and we want to work with the angles in the standard position. And when we start this today, what we're going to do is basically, I'm going to remind you of the exact same thing you did in geometry way back when you had to draw these in standard position. So standard position just means we always start on the positive x-axis with our angle, and then we do our rotations from there. And then, like it says, we want to find coordinates of points on the unit circle. That's probably going to be tomorrow. We probably won't have time for that today. So in the getting ready, the blue arrow is fixed to the x-axis. That is always how we want our angles to start. That's called the initial side of our angle, and it's always going to be on the positive x-axis. And then what we do is we figure out, how can I move one of these arrows to get a terminal side to show, hey, this is the angle that I want to have. And what this says is the blue arrow is fixed to the x-axis. The blue one's not going to move. You can turn the red one, kind of like a spinner, counterclockwise about the point O, the origin. If the red arrow contains one of these points, 0, 1, 2, 2, negative 3, 3, negative 1, 0, or 5, 0 when it stops, for which point would the angle formed by the red and blue arrows have the greatest measure? Well, I don't know. I better graph them on here and see. 0, 1, 2, 2, negative 3, 3, negative 1, 0, and 5, 0. Well, 5, 0, the arrow's right over the top of the other one. That's 0 degrees. It's not even really forming an angle. Now if I draw it through here, I can see, well, there's a bigger one over here, and there's a bigger one yet going this way. So that would be the one I would want to use. And that's my negative 1, 0 that creates a straight line, which is a 180-degree angle. Now, what if we had started by going downward? Well, you can't do that, because it turns out that positive angles are formed by a counterclockwise motion, and that negative angles are formed by a clockwise motion. It's very European. Everything feels backwards to us. It's kind of like the quadrants. You know how they label the quadrants 1, 2, 3, and 4. So it's that counterclockwise motion that gives us the positives. So down here, what we're doing is we're just looking at our angles and saying an angle in the coordinate plane is in standard position when the vertex is at the origin. One ray is on the positive x-axis. The ray on the x-axis is called the initial side. That's where we start. And the other ray is called the terminal side of the angle. Terminal just means it stops. So we're all going to start at the exact same place, but we need to stop on the terminal side. And the measure of an angle in standard position is the amount of rotation from the initial side to the terminal side, positive by going counterclockwise and negative by going clockwise. So essential understanding down here says the measure of an angle in standard position is the input for two important functions. The outputs are the coordinates called cosine and sine. And they are the points of they actually will end up being the points on the terminal side of the angle. 1 unit from the origin. Now that's really important, because what that makes for us is called the unit circle. When we center a circle at the origin and then go out 1 unit in all directions, we have formed the unit circle. And when that happens, each point that we find on those terminal sides can be represented by their two trait functions, cosine theta and sine theta, whatever it may be. So it links this all together with what we know about triangles, and now we're doing that in a circle, and that helps us get a lot of exact measurements, and it makes those measurements really, really nice. So that's what we're going to investigate over today, tomorrow, and the next day is, how are we going to get this going? All right. The measure of an angle, positive when the rotation from the initial side to the terminal side is counterclockwise. Like I said, that's kind of counterintuitive for us because we think clockwise should be positive. The measure is negative when it's going to be clockwise. So notice the little arrows that help us figure out, oh, this one's going counterclockwise, that must be positive. And we want to make sure that when we draw our angles, we also give those little arrows so that they can see, hey, this one is counterclockwise and this one is clockwise as they go through it. Otherwise, you could draw what you believe to be a 120-degree angle, and somebody else has another one in the totally wrong place because of just a positive or a negative. And then all of your trait functions would be off, and that would be very bad. So now what we're going to do let's just start off by identifying some angles. So this one starts standard position, goes this way because there's a little arrow there to show me that, and gives me this terminal side. How many degrees is that? 90. Yeah, almost 90, 90, 90, 90. You see the perpendicular lines there? It's 90 degrees. Now, for B, we can do better than, well, I think it's here. And here's why we can do better than that. One of the things we learn about in pre-calculus is drawing reference triangles. And reference triangles are always formed with the x-axis, always with the x-axis. And then I realized, well, if this is -2, -2, that means that was -2 and that was -2. That's one of our special triangles. Which one is it? It is a 45, 45, 90. That's because this is a right angle, and the only way that this can come out to be a right triangle that has two sides that are the same length is if those angles are 45 degrees. So I'm going to put a little theta in here, but I'm going to come out here and make it big enough that you can see it. That means that's a 45-degree angle. So now we can say, okay, well, they went this way, which means the angle is what? Negative. And they went past 90, and how far past? Well, if this is 45, what's this? 45. That's a -135. And we are absolutely certain about that because of what we know about the 45, 45, 90 triangle. It has to be. Got it down here says, what is the measure of this angle? Well, we go through the same thing and say, you know what? There's my reference triangle. Hey, this is 45 degrees in here. Is that -135? No, it's not. Why not? Counterclockwise this time. Yeah, counterclockwise. So 180 plus another 45, what do we get? 225 degrees for that angle. So we need to know whether or not we're going clockwise, counterclockwise to determine what we have for that angle. Now, this is just sketches, And we do need to make our little X and Y Cartesian coordinate plane here, so just take a second. Draw some of those. Now, before I draw, I always think to myself, do I know where I'm going? 36 degrees. Clockwise or counterclockwise? Counterclockwise. Am I going to make it all the way up? No. Am I going to make it halfway up? No, because it's less than 45. So I'll just kind of sketch, look something like that, but I always make sure that I label that so that if somebody's grading my paper, they can see I made an attempt. I'm trying to show you that's 36 degrees. I don't have a protractor, but close. All right, then we go to this one. We go in clockwise or counterclockwise? Counterclockwise, quite a ways, aren't we? All right, let's see. We'd have to go 90, 180, 270, and how much more than 270? Halfway, another 45 degrees. But now, if somebody looks at this, they're not going to know that I didn't want this one, right? So that's where the arrow comes in. So I make my little spiral and show them the arrow to show what's going on there. BJ, pay attention up here. Negative 150. Negative tells us we're going where? Clockwise. All the way down? And then some? Okay, so how much is the then some? Another 60? So we are just approximating. I'm not going to give you protractors to go through and do this. Now, before anybody turns the page, 43210, Lean, how do you feel about drawing your own angles? Do any of you remember this from geometry? Let's start to come back a little bit. Okay. So we're going to skip A, B, and C and doing some more drawing. And we're going to go down here and talk about two angles in standard position that are coterminal. Coterminal means they land in the same spot. That terminal side lands in the same spot every time. So I think, well, how am I going to make that happen? Like it says here, this is 135 and it is negative 225 degrees. How do you get that to happen? Well, you have a terminal side on your angle. And if you want to go all the way around and land in that exact same spot, how many degrees would you need to make that happen? Go all the way around the circle. How many degrees have you gone? 360. So what we have to do is add or subtract multiples of 360. Add or subtract multiples of 360. So I want you to look at problem 3. It's a multiple choice problem. Tell me which one of those will not land in the same spot as the other 3. Which one's out? 60 degrees. First of all, there's no way negative 60 and positive 60 are landing in the same spot. There isn't. So you know it's one of those that's out. If you take 300 and subtract 360, you get negative 60. And yeah, I know I'm closing in on it here. There we go. You can do all of this now. Sorry, I had to get those tests back. It's been so long, and I just felt like if I didn't give them back by now after spring break, nobody was even going to remember we'd taken them. And hopefully, because somebody this morning said there's only 40-something days of school left. So, no illnesses, everybody stays well.